Hello everyone, I'm Shaozhen Xu from China. I'm now working as an assistant researcher in Nanjing University. The title of my talk is the Decay Estimate for Degenerate Oscillatory Integral Operators. This talk serves as an introduction to such a subject. In the last section, I will also give some results based on our joint work with Zuoshunhua and Dunyan. Okay, this is the outline of my talk. First, I will introduce the motivation of such a subject. This part mainly contains the transition from scalar oscillatory integrals to oscillatory integral operators. Next, we focus on the decay estimate for degenerate oscillatory integral operators in one dimension. The progresses on R2 and RP decay estimate will be presented, and our main results will be included in the subsection for the argument. Okay, let's start with the motivation. The classical oscillatory integral is an integral with integrand e to the power I lambda capital S of y multiplied by a smooth cutoff psi of y. For such an integral, a central topic is to describe its behavior as lambda tends to infinity. Let's observe the integral. The frequency of the integrand increases as lambda increases, so we may design a decay in lambda with an optimal power. In fact, by simple integration by parts, we have such a theorem. It says, if the gradient of the phase function does not vanish in the support of psi, the integral decays in lambda with an arbitrarily large power, capital N. Obviously, the points making the gradient of the phase function vanish are very important, so we call these points critical points of a capital S. In other words, the theorem tests that if the phase function has no critical point, I of lambda decays rapidly. The existence of a critical point results in the failure of integration by parts. So, if the critical points of the phase function have good properties, can we still get the decay estimate for I of lambda? The classical stationary phase method gives an affirmative answer. If the Hessian of the phase function at a critical point does not vanish, we say that the critical point is non-degenerate. Stationary phase method, in fact, gives the precise asymptotics of I of lambda. Naturally, the sharp decay rate is minus n over 2. The non-degenerate case has been discussed. How about the degenerate case? If the phase function is a real-analytic, Arnold had a hypothesis. It asserted that the sharp decay rate of I of lambda is determined by the Newton distance of the phase function. Here, Newton distance is a concept in algebraic geometry. We will introduce it later. This hypothesis was confirmed by Vachenko in 1976. In the proof, Vachenko made use of Hronaka's celebrated theorem on resolution of singularities. Now, we introduce two concepts in algebraic geometry, Newton polyhedron and Newton distance. A real-analytic function, capital S of y, naturally has a Taylor expansion, the summation of a capital C sub alpha, multiplied by y to alpha. The Newton polyhedron and the Newton distance of capital S are given as follows. The fancy definitions like heuristics. Next, we use an example to demonstrate these two concepts. Here is the example. Capital S of xy equals x squared multiplied by y to the power 4 minus x cubed multiplied by y squared plus x to the power 5 multiplied by y plus a high-order error term. Clearly, capital S is a two-dimensional real-analytic function. The coefficients capital C sub 2, 4, capital C sub 3, 2, and capital C sub 5, 1 are non-zero. They correspond to the three vertices capital V sub 1, capital V sub 2, and capital V sub 3. According to the definitions, the blue area is the Newton polyhedron of a capital S. The line P equals Q intersects the Newton polyhedron at the point 8/3, 8/3. So, the Newton distance is 8/3. We should point out that the figure in this page belongs to Dr. Le Xiao. Modeled on the scalar oscillatory integrals, we can give the definition of oscillatory integral operators, capital T sub lambda. It is a functional on any RP space. Now, we give a brief summary. For the scalar oscillatory integrals, the hypothesis of Arnold connected the decay estimate with the Newton distance of the phase function. The connection between oscillatory integral and oscillatory integral operator is natural. So, what's the relation between the decay estimate for the operator and the Newton distance? Observe the graph. A natural question is what's the relation between the sharp decay rate of capital T sub lambda and the Newton distance? We first investigate the decay estimates on R2 space. For the non-degenerate case, Haumann's lemma gives the sharp decay estimate, and the sharp decay rate is minus n/2. One can compare this theorem with the stationary phase method. They are similar. Notice that in this theorem, the dimension n is arbitrary. However, if the phase function is degenerate, it is hard to obtain the decay estimate. In the past 30 years, only the one-dimensional cases are totally understood. Feng and Stein made a breakthrough in 1992 for a class of homogeneous polynomial phases. They gave the sharp decay, and the decay rate is minus 1/m. Look at the theorem. The restrictions on the index M seem complicated. Actually, it is more natural to realize the restrictions from the perspective of a Newton polyhedron. They make sure that the Newton distance is exactly m over 2. In 1994, they extended this result to all homogeneous polynomial phases. The purpose of the restrictions on the indices is also to make sure that the Newton distance is m over 2. In 1997, they succeeded in extending this result to all real-analytic phases. They confirmed that the sharp decay rate is determined by the reduced Newton distance. Roughly speaking, we can regard the reduced Newton distance as the Newton distance because they are equal when the phase function has no pure x term or y term in the Taylor expansion. Later, Richkoff and Greenblatt together extended this result to all smooth phases. Look at this theorem. It is similar to the real-analytic case. Since the decay estimates on R2 space has been totally understood, it is natural to extend this result to more general function spaces. For example, LP spaces. The Euro-Ritz-Thorin interpolation may give a LP decay estimate, but it's not sharp. Now, we introduce the progresses on sharp LP decay estimates. If the phase function is a homogeneous polynomial, and its first and last coefficients are non-zero, Yang proved that the sharp decay on R2 space can be preserved on more general LP spaces. Later, Shi and Yan extended this result to all homogeneous polynomial phases. At last, Xiao obtained the sharp LP decay estimate for all real-analytic phases. Here, I want to say more about Xiao's proof. Xiao's proof relies on Newton-Poiseuille algorithm. Such an algorithm was usually used to resolve singularities of plane curves. Roughly speaking, after carrying out the algorithm on the phase function, it behaves like a monomial in certain good areas. Next, we give an example to demonstrate this heuristic. Look at the figure. In the good areas, capital S behaves like a monomial. For example, in the bottom good area, the size of x is much larger than the size of y. So, capital S of xy can be seen as a monomial minus x to the power 6. Good areas are certainly good, but how about the bad areas? Actually, we can carry out a stopping time argument on those bad areas. Unfortunately, the iteration will terminate in finite steps. It should be pointed out that the figure in this page belongs to Dr. Le Chaoxiao. Now, we consider Xiao's result in another way. In fact, inserting a damping factor into the operator capital T sublambda we can get the operator W sub z. The damping factor, the absolute value of D to the power z, is related to the phase function. Clearly, if z equals 0, we recover T sub lambda from W sub z. This reminds us of applying complex interpolations to get the LP decay estimate. To analyze the damping factor, we introduce some fancy notations. According to Poiseuille expansion theorem, we can write the Hessian of the phase function as such a product. The only unclear elements are the Poiseuille series R sub nu of x, but luckily, they are closely related to the Newton polyhedron of the Hessian. We order the leading exponents of all roots from smallest to largest. We use capital psi to denote the cluster of R sub nus which have same leading exponent. We use capital N to denote the number of roots in a specific capital psi. So, the vertices capital A sub r, capital B sub r of the Newton polyhedron can be given by capital N. For convenience, you can just remember the definition of capital A sub r, capital B sub r, and ignore the rest. Okay, let's continue. We now turn to the damping factor, capital D of xy. Look at the expression. It is in fact a partial product of the Poiseuille expansion. It varies as the index R varies. For the damped oscillatory integral operator, capital W sub z, if the real part of z takes the form shown in this page, we have the sharp L2 decay estimate. For capital W sub z, there is no appropriate boundedness result on critical spaces. So we divide it into three parts: capital W sub z to 1, capital W sub z to 2, capital W sub z to 3, and establish different boundedness results individually. We can see from the theorem that capital W sub z to 1 is of a weak 1 type. Capital W sub z to 3 maps L1 to itself. If the damping factor does not vanish on a single curve, then capital W sub z to 2 is bounded from L1 to itself. Otherwise, it is bounded from a varied Hardy space to L1. Now, we have both L2 estimates and an endpoint estimate. By interpolation, we can give an equivalent formulation of Xiao's result. And our result is formulated in terms of the vertices of the Newton polyhedron. Okay, this is the end of my talk. We can stop here. Thanks for your attention.